Good morning, students. In this video session, I'm going to explain you about the small signal analysis of a differential amplifier. The mode of operation of the differential amplifier and its application has been discussed in the last class, and now we are going to look at the small signal analysis of a differential amplifier. So before going to the small signal analysis of a differential, let us recollect the things what you have seen for the differential amplifier. So what is a differential amplifier? The amplifier which amplifies the difference between two input signals is called a differential amplifier. Here, the differential amplifier circuit is shown where the emitter of both the transistor Q1, Q2 are tied together and given to a common current source. So we can call this differential amplifier to be a emitter coupled differential amplifier, and the assumption has to be made for the analysis of the differential amplifiers are the early effect, that is VA, is considered to be infinite. So the output resistance of the transistor parameters also considered to be infinite, and we are not going to include in the transistor part. And next, the constant current source is not the ideal case, so we are going to represent this constant current source by the finite output resistance R naught. And the condition for the AC analysis is we have to short circuit the supply that is present in your transistor in your circuit diagram. So your VCC and VE is going to be short circuited, and the remaining part is going to be drawn as if so the VB in parallel with the VB in we are going to connect the RB, and we are going to replace the transistor Q1 by its transistor parameters where from the between the base and emitter part a resistance R pi will be present, and the voltage across this resistance is going to be V pi 1. And if we come to the transistor Q2, the transistor parameter between the base and emitter is going to be replaced by the transistor by its resistance R pi with the voltage present V pi 2 at parallel to it, and from the collector to the emitter terminals, from the collector to emitter terminals, we are going to have a transconductance current source with the transconductance Gm into V pi 1. Now let us look at the small signal circuit diagram of a differential amplifier. See, here comes the small signal equivalent circuit of a differential amplifier. As I've already told, the VB1 has been VB1 in series RB is present, and the transistor parameters are being replaced by R pi. Between the base and emitter terminals, we are having a resistor R pi, and the voltage across the resistor is given by V pi 1. And between the transistor Q2 base and emitter, it's been replaced by the resistor R pi with V pi 2. And from the collector to emitter terminals, we are having a current source GM V pi 1 and GM V pi 2. And we are going to take the output across the collector terminals. So the collector 1 is given by Vc1, the voltage at collector 1 is given by Vc1, and the voltage at collector 2 is given by Vce2, and the other end of both the collector resistor has been grounded. Now let us look the analysis of a differential amplifier. So I'm going to consider a node over here. Consider a voltage at this node is given by is being represented by VE. The first step is I want to find what is the output voltage that we are going to present in the circuit, and the common mode gain, a differential mode gain is going to be calculated. From the common mode gain and differential mode gain derivation, we are going to find what is the CMRR of a differential amplifier. So the first step is apply KCL at the emitter low node. So if you apply the KCL at this emitter node, so what are the current that is entering the node and what are the current that is leaving this nodes are? The current enters the node can be written as V pi 1 divided by R pi plus Gm V pi 1 plus Gm V pi 2 plus V pi 2 divided by R pi. So these are the four current that is entering this node, and the current which leaves this node is given by V divided by R naught. So the equation which we got here is V pi 1 by R pi plus Gm V pi 1 plus V pi 2 by R pi plus Gm V pi 2 is equal to VE by R naught. So from the equation, I'm going to take the V pi 1 outside. So remaining I'm writing as Gm plus 1 by R pi plus from the two equations I've taken the V pi 2 out. So I'm writing the remaining term as Gm plus 1 by R pi equal to V by R naught. The next step is I just cross multiply Gm with R pi, and V pi 1 into Gm R pi plus 1 divided by R pi plus V pi 2 into Gm R pi plus 1 divided by R pi. So we already know that Gm into R pi can be written as beta. So I'm going to replace the term Gm R pi by beta. So V pi 1 into 1 plus beta divided by R pi plus V pi 2 into 1 plus beta divided by R pi will be equal to V by R naught. Let us consider this is equation number 1. Next, from the figure, we can find that what is my V pi 1 by R pi? What is my V pi by 1 by R pi? What is the current that is flowing through this resistor V pi 1 by R pi? So I can write this equation as we are having two voltages at this node, one voltage here and one voltage. So the current flowing through this resistor can be written as VB1 minus VE divided by RB plus R pi. That will give the current that is flowing through between these two nodes. And the same thing similarly we can apply for the other case. So if I want to find what is the V pi 2 by R pi, so it is nothing but it's given by VB2 minus VE divided by the sum of two resistors, that is RB plus R pi, that will give the current that is flowing through this resistor. So I can write the equation as V pi 1 divided by R pi will be equal to VB1 minus VE divided by RB plus R pi, or V pi 2 divided by R pi is equal to VB2 minus VE divided by RB plus R pi. So I'm going to consider this is equation number 2. Now I'm going to substitute the equation 2 in equation 1. So in the place of the V pi 1 by R pi and V pi by 2 by R pi, I'm going to substitute this equation. So 1 plus beta into VB1 minus VE divided by RB plus R pi plus 1 plus beta divided by RB plus R pi into VB2 minus VE is equal to VE by V naught. So if I solve this equation of bringing all the other terms to the other one and VE by R naught, I'll be getting the equation as 1 plus beta divided by RB plus R pi into VB1 plus VB2 minus 2VE into 1 plus beta divided by RB plus R pi will be equal to VE by R naught. So I'm taking all the VE terms to the other side. So from this, I'm cancelling this R pi plus RB and R pi plus RB. So by solving this equation, I got VE is equal to VB1 plus VB2 into 1 plus beta R naught divided by this term, which is given by R pi plus RB plus 2 into 1 plus beta into R naught. And beta 1 plus beta has been cancelling. So I'm getting the final equation for my emitter voltage as V is equal to VB1 plus VB2 divided by 2 plus R pi plus RB divided by 1 plus beta into R naught. This is going to be considered to be equation number 3. The next is I'm going to consider here as a differential amplifier as one-sided output at the collector of Q2. So I'm going to take the output only from the collector of Q2. So my V0 I can write from the equation as V0 is equal to the voltage VC2 is nothing but I into R formula, where I is given by GM V pi 2 into R is given by RC. So V0 can be written as minus Gm V pi 2 into Rc. The minus indicates that the current is flowing in opposite direction. Now I'm going to substitute the equation 2 in 4. That is, in the place of V pi 2, I'm going to substitute the equation 2 in 4. Okay. So what is the equation number 2? The equation number 2 is given by this equation. I'm going to substitute V pi 1 equation is equal to R pi into this equation. I'm going to substitute in the place of V pi 1 or V pi 2 here. So V naught is equal to Gm R pi VB2 minus VE divided by RB plus R pi into RC. So we know that I'm going to replace my Gm into R pi as a beta value. So we know the equation we got is minus beta RC into VB2 minus VE divided by R pi plus RB. This will give the equation number 5. Now I'm going to substitute the equation 3 in 5. Substituting equation 3 in 5, that is, in the place of the VE, I'm going to substitute the equation 3 over here. So VE is given by this equation. So V0 is equal to minus beta RC into VB2 minus, I have substituted the VE equation, VB1 plus VB2 divided by 2 plus R pi plus RB divided by 1 plus beta into R naught, the whole divided by R pi plus RB. The next step is I'm going to solve this equation to get my final equation of my V naught, that is minus beta RC by R pi plus RB. So I just cross multiply this one. I just cross multiply this equation and have written it as VB2 into 2 plus RB plus RB. By solving this one further, I got a V naught equation as minus beta RC divided by R pi plus RB into VB2. From this two things, 2 VB2 minus VB2 will give a VB2. So here I'm getting VB2, here a VB2. From this I've taken commonly VB2 outside. So I can write the remaining equation as 1 plus R pi plus RB divided by 1 plus beta R naught minus this VB1 term comes here, and the denominator I'm writing as sub. So this will give my V naught equation, which is given by the equation which has been noted by the equation number 6. The next step is, for the ideal current source, I'm going to consider the output R naught to be equal to infinite. So considering the ideal current source equation, so I can replace my equation, I can rewrite my equation number 6 as, replacing that R naught is going to be this term, this two terms, this complete term, this term is going to be neglected from the circuit since I'm considering R naught is equal to infinite. So the remaining I can write as V naught is equal to minus beta RC into VB2 minus VB1, the whole divided by R pi plus RB. So we got the equation like this, and we know that for the differential mode input, the differential voltage is given by the difference between two input voltages, VB1 minus VB2. From this we can find the differential mode gain is given by the equation output voltage divided by the difference between two input voltages. This VD is given by VB1 minus VB2. So I have substituted in the place of V0 the equation number 7, and in the place of VD I've substituted the equation number 8 over here. So since here the VB1 is in the terms of VB1 minus, I'm taking the minus term outside and I've written that one as minus of VB2 minus VB1. These two terms are getting cancelled. So I can write my differential mode gain is equal to beta RC divided by 2 into R pi plus RB. So this is one way of finding the differential amplifier. Now we are going to go for an alternate way of finding what is the differential mode gain equation and what is the common mode equation we are going to get it. So for that, the above equation is identical to the equation obtained from the voltage transfer characteristics. So already in the last class I have discussed about the DC transfer characteristic of a differential amplifier. From the DC transfer characteristics we can write two voltages. One is differential voltage, another one is common mode voltage. The differential voltage is given by VB1 minus VB2, and the common mode voltage can be written as average of two input signals, which is nothing but VB1 plus VB2 divided by 2. So from this two equation, I'm going to derive VB1 equation and VB2 equation. So from the equation VCM, I got a VB2 equation as 2 times 2 into VCM minus VB1. So I'm going to substitute this VB2 equation in this place. So VD is equal to VB1 minus, I'm substituting this equation over here and I'm solving it further, and I am getting the equation as VB1 is equal to I'm bringing the other terms to the other side. So VB1 is equal to VD divided by 2 plus VCM. This is the equation number 1. So the similarly I can get, instead of substituting VB2 here, I can go with the VB1. So VB1 can be written as 2 times the VCM minus VB2. If I substitute this one in this place of VB1, I'll be getting the other equation for VB2, which is given by VB2 is equal to VCM minus VD by 2, and VB1 is equal to VCM plus VD by 2. So these are the two equations I can get from the general equation which is being derived from the DC transfer characteristic of a differential amplifier. The next step is I'm going to substitute the equation number 9 and 10 in equation 6. That is, already we got the equation for the V naught. In the place of VB1, VB2, I'm going to substitute these two equations in equation number 6. So V naught is equal to minus beta RC divided by R pi plus RB, and in the place of VB1 I've substituted as VCM, VB2 I've substituted as VCM minus VD by 2, and in the place of VB1 I've substituted as VCM plus VD by 2, and the remaining equation. By further simplifying this equation, further doing all the simplifications of taking from this equation, so what has been done is I'm just substituting this equation by this equation minus this equation divided by this equation. These two are being solved separately, and we are getting as 1 plus beta into R naught, 1 plus beta into R naught, both are getting cancelled. So further simplifying, I got the equation of V naught is equal to beta RC divided by 2 into R pi plus RB into VD minus GM RC divided by 1 plus 2 into 1 plus beta R naught divided by R pi plus RB into VCM. So I'm going to compare this equation number 11 now. This equation number 11 I'm going to compare with the general equation of a differential amplifier, which is given by V naught is equal to AD into VD plus ACM into PCM. So this is the general equation. The output voltage equation for the differential amplifier can be written as V naught is equal to AD into VD plus ACM into PCM. So if I compare this equation number 11 and 12, in the place of AD, I got the equation as beta RC divided by 2 into R pi plus RB. In the place of ACM, I got the equation as minus GM RC divided by 1 plus 2 into 1 plus beta R naught divided by R pi plus RB. So I can write the differential mode gain as beta RC divided by 2 into R pi plus RB, and the common mode gain can be written as minus GM RC divided by 1 plus 2 into 1 plus beta R naught divided by R pi plus RB. And these are the general terms. Transistor parameters we already solved in the transfer characteristic curve, but GM is given by beta by R pi, or GM can also be written as the collector quiescent current divided by the thermal voltage, or ICQ can be written as IQ by 2. I'm going to substitute all these equations in this place of a differential mode and the common mode, in the place of a beta and in the place of a GM. So the differential mode gain, if I consider the base resistance to be equal to 0, I can write the differential mode equation as, I'm going to consider this RB as 0. So I'm writing a differential mode gain as beta RC divided by 2 into R pi. So I'm going to replace my beta by GM beta by R pi as GM RC divided by 2, and further GM can be replaced by ICQ divided by Vt, and ICQ divided by Vt can be written again, can be replaced by the term called as IQ by 2. So ICQ can be written as IQ divided by 2. So this is the final equation for the differential mode gain. And for the common mode gain, the same procedure is being followed. The common mode gain is given by the equation minus GMRC divided by 1 plus 2 into 1 plus beta into R naught divided by R pi. Here I am replacing the place of GM as ICQ divided by Vt, and further ICQ is being replaced by IQ by 2, and in the place of R pi I've replaced as GM by beta, and GM is further replaced by IQ divided by 2 into Vt. So I got the equation for the common mode gain as minus IQ RC divided by 2 Vt divided by 1 plus beta IQ R naught divided by Vt into beta. So from the differential mode gain and the common mode gain, we can calculate what is the common mode rejection ratio. So the common mode rejection ratio is nothing but the ratio between the differential mode gain divided by the common mode gain. So I'm substituting in my differential mode gain equation and common mode gain equation here. So I'm cancelling all the other terms. So I got the final equation of a common mode rejection ratio for the differential amplifier is given by the formula 1 by 2 into 1 plus beta IQ R naught divided by Bt into beta. So okay students, in this class I've discussed about what is a differential amplifier, small signal analysis, and how we are deriving the differential mode equation and a common mode equation from the small signal equivalent circuit, and from the differential mode and common mode gain. Finally we got the equation for the common mode rejection ratio. Thank you.